Hello, and a very soft welcome to the Midnight Scientists. You found your way to a quiet corner of the cosmos, a place where we ponder the universe's great whispers at a pace designed for comfort, for letting the day dissolve. Our purpose here is wonderfully gentle, a slow exploration of grand ideas, perfect for unwinding your mind, relaxing your body, and perhaps even drifting into slumber long before our journey ends. Tonight, our voyage is especially vast. We are embarking on a cosmic tour of everything, from the shimmering dance of the smallest particles to the silent, sprawling architecture of galaxies. We will float through it all with a serene calm. There is no need to rush, no need to grasp. Just allow the ideas to wash over you like gentle waves. Now, a gentle warning. My deepest hope is that this journey isn't too interesting. The goal here is tranquility, a soft path to sleep, not a lecture that keeps you awake. But if you do find your mind alight, pondering the nature of space-time as the world outside sleeps, well then, you will have some beautiful cosmic truths to whisper into the quiet of the night. Before we properly begin, I would love to feel our connection across this spinning globe. Where in the world are you listening from tonight? What time is it in your little corner of the world? Let me know in the comments. It is a quiet joy to imagine this peaceful broadcast reaching so many different moments. A sunrise in one place, a deep midnight in another. And if you find solace in this gentle voyage through the stars, whether you are awake at the end or fast asleep by the second chapter, please consider leaving a like or subscribing. Your support helps this peaceful space continue to exist, and for that, I would be truly and deeply grateful. Now, as we prepare to drift away, a soft reminder. Nothing in this video is meant as medical advice. If sleep is a persistent trouble, or if you have any health concerns, the kindest thing you can do for yourself is to speak with a professional. All right. Let your body grow heavy and soft. Let your mind loosen its grip on the day. We are about to float into the stars together, and there is no need to hold on at all. Let us begin our descent. Down, down, past the world of the visible. Smaller than a thought, smaller still. Picture an atom, already a universe of impossibly tiny. Now imagine dissolving through its gossamer cloud of electrons, plunging deep into the dense, humming heart of its nucleus. Keep going, deeper and deeper, until the very fabric of reality begins to fray. This is where our journey begins, in the quantum realm, the subatomic underworld where all of existence is born. It is not just small here, it is fundamentally strange. It's a place where the familiar laws of physics gently surrender to a new kind of logic. The quantum world seems to operate on a set of rules written in a language we are only just beginning to translate, a language of maybes and probabilities. It is a place where particles are also waves shimmering between states of being, where absolute certainty is a forgotten luxury, and where cause and effect seem to wander off for quiet contemplation. It is a realm of beautiful, bewildering weirdness, and it is the foundation of everything. So what are we truly made of at this most fundamental level? Everything in the universe arises from what we call fundamental particles. But do not picture them as tiny marbles or motes of dust. A better image is to think of them as ripples on invisible fields that permeate all of space. Imagine the silent, glassy surface of a vast, still pond. Now imagine a single pebble dropped into it, sending a ripple spreading outward. That ripple is the particle, and the pond is a quantum field, an invisible ocean of potential that exists everywhere, always. This is the modern understanding. Particles are not things, so much as they are events, tiny, localized excitations, like a brief, focused thought in the mind of the cosmos. Consider the electron, a particle so familiar to us. It is simply a ripple, a tiny, energetic blip in something called the electron field. That field is everywhere, silent and unseen. But when it is excited in just the right way, a particle we call an electron blossoms into existence. And then there is the photon, the very particle of light. It is a ripple in a different field, the electromagnetic field, which carries warmth and vision across the void. And we cannot forget the quarks, the tiny, whimsical building blocks of protons and neutrons, the heavy stuff at the heart of atoms. Quarks come in 6 flavors, with names that sound like they were pulled from a dream: up, down, top, bottom, charm, and strange. These aren't flavors you can taste, of course. They're simply different states of being. Quarks are intensely social. They are never found alone. They cluster in groups of 2 or 3, bound together by carrier particles called gluons. The name is perfect, for gluons are the cosmic glue of the universe. These tireless little messengers are responsible for the strong nuclear force, one of the 4 fundamental forces of nature. This strong force is what holds atomic nuclei together, overcoming the immense electrical repulsion of all those positively charged protons packed into a tiny space. Without the persistent work of gluons, all atoms would instantly fly apart. The universe as we know it would simply dissolve. While we are here, let us gently take inventory of the forces. There are 4. First, the strong nuclear force we have just met. Second is the electromagnetic force, the author of electricity, magnetism, and light itself. Third, the weak nuclear force, a subtle but crucial player in radioactive decay and the fusion that powers the stars. And finally, gravity, the gentle, persistent force that holds your body softly to your bed, that keeps the moon in its silent orbit, and that gives black holes their profound mystery. Oddly, of all the forces, gravity is the one we understand the least at this quantum scale. It is by far the weakest of the 4. But when you gather enough mass, like a planet or a star, its effects become dramatic and inescapable. In the tiny world of particles, however, the other forces reign supreme. For instance, the strong force is about 10,000 times more powerful than the electromagnetic force, which in turn utterly dwarfs the force of gravity at the atomic scale. Now, let us speak of uncertainty. Here in the quantum realm, nothing is ever truly still or definite. This is not a failure of our instruments. It is a fundamental feature of reality itself. Uncertainty is woven into the very fabric of existence. According to Heisenberg's uncertainty principle, you cannot simultaneously know both the exact position and the exact momentum of a particle. The more you know of one, the less you know of the other. It becomes a blur, a haze of possibility. Imagine trying to capture a perfect photograph of a hummingbird's wings. You can have a sharp image of their position at one instant, or a blurry image that tells you about their motion, but never both at once. Now, apply that principle not to a bird, but to the very essence of matter, and you begin to feel the shimmering, unpredictable nature of this world. Particles exist in a state of constant, gentle flux, a soft dance between being and non-being. It is as if the universe is playing a gentle game of hide-and-seek with itself. And this leads us to quantum superposition, the idea that a particle exists in all possible states at once, until the moment it is observed. This is not just a theory. It is a demonstrated reality, proven time and again in careful experiments. The most famous illustration of this is Schrödinger's thought experiment with the cat. You know the story. A cat in a sealed box, its fate tied to a random quantum event. Until the box is opened, quantum mechanics says the cat is not one or the other. It is in a superposition of both, alive and dead. The point is not that we simply don't know its state. The point is that in the quantum description, it truly occupies both states simultaneously until an observation forces a choice. Of course, this experiment has never been performed on a real cat. It was designed to show just how bizarre the quantum world is when we try to apply its rules to our everyday lives. Cats, thankfully, follow their own laws of physics, which mostly involve the strategic relocation of objects from high shelves in the dead of night. And let us not forget quantum entanglement, perhaps the most profound mystery of all. When two particles become entangled, their fates are linked. Their quantum states are intertwined, no matter how far apart they travel. If you measure a property of one particle, you instantly know the corresponding property of its partner, even if it is on the other side of the galaxy. Einstein famously called this spooky action at a distance. He was unsettled by the idea, but it has been proven to be real. Entanglement happens. But how? How does one particle know what happened to the other instantly, faster than light could travel between them? The best way to think about it is that they are not two separate things that communicate. They are two parts of a single, unified quantum state. When you observe one, you are not sending a signal to the other. You are simply revealing a piece of a puzzle that was already whole and interconnected. The answer was there all along, waiting to be seen. If your mind feels a little fuzzy at this point, that is perfectly natural. Even the physicists who work with quantum mechanics every day describe it as something you never truly understand. You just get used to its beautiful strangeness. And what about the space in which all this occurs? Is empty space truly empty? Not at all. In the quantum view, even a perfect vacuum is a bubbling, seething cauldron of activity. Virtual particles constantly pop into existence, borrowing a tiny amount of energy from the vacuum for a fleeting moment before vanishing back into nothingness.
This constant fizz of creation and annihilation is called quantum vacuum fluctuation, and it has real, measurable effects. One such effect is the Casimir effect, where two uncharged metal plates placed incredibly close together in a vacuum will be gently pushed toward each other by the fluctuations in the space around them. It is as if the universe cannot bear to be perfectly still. Even in its quietest corners, it hums with a restless, invisible energy. The quantum world may sound like a dream, but its principles power so much of our waking world. Lasers, semiconductors, the computer or phone you're using right now, all of these technologies depend on our understanding of quantum physics. Without it, there would be no sleepy YouTube videos about the mysteries of the universe. Yet, for all our progress, the quantum realm remains shrouded in mystery. The measurement problem, for instance, still haunts physicists. What is it about observation that causes a quantum system to collapse from a cloud of probabilities into a single definite state? Is consciousness involved? Or is the universe simply keeping some secrets to itself? No one knows for sure, but we continue to listen, to explore, because understanding this tiny, foundational layer of reality is not just about the small things. It is about uncovering the fundamental rules that shape everything. From the soft glow of your screen to the distant, silent stars, it all begins here, in a place where particles shimmer like ghosts of possibility, where invisible fields ripple through the vacuum, and where reality itself seems to be woven from threads of probability more than certainty.
It is a strange and beautiful world, humming quietly, peacefully beneath everything. From that shimmering quantum foam, let us rise just one level, to the world of the atom. They are the silent, patient architects of the universe. Everything you can see, everything you can touch, is built from them. The soft fabric of your blanket, the air you are gently breathing, the distant stars. It is all, every last speck, a masterwork of atomic construction. But do not let their prevalence fool you into thinking they are simple. Atoms are miracles of cosmic engineering. They are impossibly tiny, yes. A single grain of sand holds more atoms than there are stars in the known universe. Yet each one is an intricate, balanced system, holding within it the memory of ancient stars and the promise of all chemistry. The name atom comes from the ancient Greek word atomos, meaning indivisible. The philosophers who coined it imagined atoms as the final, uncuttable pieces of reality. But nature, as it often does, revealed a deeper layer of complexity. We now know that atoms are divisible after all. They are composed of even smaller particles, protons, neutrons, and electrons. For a gentle mental image, you can picture an atom like a miniature solar system, though the reality is much fuzzier. At the center lies the nucleus, a dense, heavy core of protons and neutrons. Far out from this core, in a vast and mostly empty space, the electrons exist.
But they do not orbit like planets on neat, predictable paths. Instead, they live in hazy, probabilistic clouds called orbitals, where we can only speak of the likelihood of finding an electron in any given place. They are a mist of potential surrounding a solid core. Let us consider the simplest atom, hydrogen. It is the lightest and most abundant element in the entire cosmos. It consists of just one proton and one electron. That is all. It is the humble, essential building block of the universe. And despite its simplicity, its importance is immeasurable. Hydrogen is the fuel of stars. It is what the sun burns in its core to produce the light and warmth that gives life to our world. If atoms were characters in a grand cosmic play, hydrogen would be the modest, quiet lead who carries the entire story. Next on the periodic table is helium, with 2 protons, 2 neutrons, and 2 electrons. Helium is like hydrogen's serene older sibling. It is gentle, inert, and famously non-reactive. It is the quiet guest at the chemical party who prefers to float peacefully in the corner. It is also what makes balloons rise and what fills the blimps that drift so silently across the summer sky. As we journey through the periodic table, atoms become larger and more complex. The number of protons in the nucleus defines the element. 6 protons make a carbon atom. 8 make oxygen. 79 give us the warm glow of gold. 92 give us the heavy instability of uranium. Each step up this ladder adds a new character to the cosmic story, with unique properties and a unique role to play. But here is a fact that can truly quiet the mind. Atoms are almost entirely empty space. If the nucleus of an atom were the size of a marble, the nearest electron would be a cloud of probability nearly half a mile away. And the nucleus itself is unfathomably dense. If you could somehow gather just the nuclei from all the atoms in a car, they would fit on the head of a pin. This is the strange, ghostly nature of the matter that makes up our solid-seeming world. It is more space than substance, held together by invisible forces. Now, let us look closer at the 3 particles. Protons, with their positive charge, live in the nucleus and give an atom its identity. Add a proton and you change the element. Neutrons live alongside them, carrying no charge. Their job is crucial. They act as a buffer, a nuclear peacemaker, adding enough of the strong force to keep the mutually repelling protons from flying apart. And then there are the electrons. These tiny, negatively charged particles are astonishingly light, and they dance in their orbital clouds. The arrangement of these electrons, especially in the outermost shell, dictates how an atom interacts with others. Electrons are the social agents of the atomic world. They are the ones that reach out, form connections, and build the intricate structures of molecules, from simple water to the complex wonder of DNA. Electrons exist in specific energy levels, or shells, like floors in a building. They prefer the lowest, most stable floor available.
But give an electron a bit of energy, perhaps from a particle of light, it can leap to a higher floor. When it eventually falls back down, it releases that borrowed energy, often as a photon of light of a very specific color. This is the secret behind the glow of a neon sign, the brilliant colors of fireworks, and the gentle, distant twinkle of the stars. The chemical behavior of an atom is driven by its desire to have a full outer shell of electrons. It's a fundamental drive towards stability. To achieve this, some atoms will give away an electron, some will take one, and some will agree to share. These interactions are what we call chemical bonds, and they're the foundation for building everything from a raindrop to a rose. In an ionic bond, one atom donates an electron to another. Sodium gives one to chlorine, and they form sodium chloride, or table salt. In a covalent bond, atoms share electrons, like two hydrogen atoms and one oxygen atom holding hands to become a molecule of water. All of these bonds, all of chemistry, stems from this simple, elegant desire of atoms to find a stable, peaceful configuration. We also find fascinating variations called isotopes. An isotope of an element has the same number of protons, but a different number of neutrons. Carbon, for example, usually has 6 protons and 6 neutrons, but an isotope called carbon-14 has 8 neutrons. It is still carbon, chemically speaking, but it is heavier and unstable or radioactive. Scientists use the predictable decay of isotopes like carbon-14 to date ancient objects, listening to the faint ticking of an atomic clock to peer into the deep past. Most atoms, however, are stable. They exist quietly, patiently, buzzing with potential, until they are called upon to become part of a leaf, or a breath of air, or a meteor streaking across the night. And here's a thought to carry you into sleep tonight. Nearly every atom in your body, heavier than hydrogen, was forged in the heart of a dying star. The carbon in your cells, the oxygen in your breath, the calcium in your bones, all were created in the unimaginable heat and pressure of stellar furnaces, and then cast out across the galaxy in cataclysmic supernova explosions. Every breath you take is filled with the ashes of ancient suns. You are, quite literally, as Carl Sagan so beautifully said, made of star stuff. The atoms that make you are ancient. They connect you not just to the Earth, but to the entire history of the cosmos. The atoms in the water you drink may have once drifted through the tail of a comet. The atoms in your body have been on a journey for billions of years, and they will continue long after we are gone, rearranged into new forms, part of new stories. So as you rest, feel the gentle weight of your body. You are not just a single being. You are a temporary constellation of countless ancient atoms woven together by the laws of physics into the beautiful, fleeting shape that is you. It is humbling, it is magical, and it is happening all the time, in everything. Atoms are not just particles, they are storytellers, carrying the history of the universe within them. And if you listen quietly enough, you can almost hear them whispering. Atoms by themselves are remarkable, ancient vessels of star-forged elegance. But the true magic begins when they interact. This is where the universe gets truly creative, cooking up everything from clouds and cacti to comets. This is the realm of chemistry. Chemistry is the story of what happens when atoms get social. It is the grand cosmic dance of the periodic table, where elements meet, connect, and transform. Imagine it as a gentle gathering. Hydrogen, the simplest guest, arrives first, essential and unassuming. Oxygen enters with a bit more flair and immediately pairs with 2 hydrogens to form water, the universe's most vital refreshment. Carbon, ever the life of the party, arrives and begins building intricate, branching structures, the very backbone of all life as we know it. This is the essence of chemistry, the science of atoms combining, sharing, and creating entirely new substances with properties their individual parts never possessed. It's like musical notes. Alone, they're just pitches, but together they can form chords, melodies, and symphonies of infinite richness and beauty. The periodic table is our guide to the personalities of these elements. Each one's character is shaped primarily by the electrons in its outermost shell, the valence shell.
These are the electrons that engage in bonding. And the driving force is a quest for stability, a full outer shell. This is why sodium, with one lonely electron in its outer shell, is so eager to give it away. And chlorine, which is just one electron short of a full shell, is more than happy to accept it. When they bond, they form sodium chloride, table salt. Separately, one is a highly reactive metal, and the other is a poisonous gas. Together, they create a stable, life-sustaining crystal. Chemistry is full of such beautiful transformations. These chemical bonds come in several main varieties. We've met ionic bonds, where electrons are transferred. Then there are covalent bonds, where atoms share electrons more equitably. This sharing is what happens when oxygen and hydrogen form water. Covalent bonds are the true team players, forming the stable backbones of sugars, proteins, and DNA, the very molecules of life. Sometimes this sharing is not perfectly equal. In a molecule like water, oxygen pulls the shared electrons a little closer, creating a slight negative charge on its end and slight positive charges on the hydrogen ends. This polarity is what gives water its amazing properties, its ability to dissolve so many things, its surface tension, and the way it forms exquisitely symmetrical hexagonal crystals when it freezes into a snowflake. There is also metallic bonding, which you can find in a copper wire or an iron beam. In metals, the outer electrons are not tied to any single atom. Instead, they roam freely in a kind of electron sea that flows through the whole structure. This is what gives metals their ability to conduct electricity and heat and their characteristic reflective sheen. Once atoms bond into molecules, the possibilities are endless. Molecules can be tiny, like the 2 oxygen atoms you're breathing right now. Or they can be staggeringly large and complex, like a single molecule of DNA, which contains the complete architectural blueprint for building an entire living organism. Carbon is the master architect of life. It can form 4 strong, stable bonds at once, making it incredibly versatile. It can build long chains, intricate rings, and complex branching structures. It is the ultimate Lego brick of the cosmos, able to build almost anything. Thanks to carbon's versatility, we have the molecules of life. Carbohydrates for energy, proteins for structure and function, lipids for membranes and storage, and nucleic acids to carry the genetic story. Even the air that fills your lungs is a quiet lesson in chemistry. It is about 78% nitrogen, a very stable and non-reactive gas, which is a good thing. It provides a calm, neutral backdrop for everything else. About 21% is oxygen, the energetic reactive gas that our cells use to release energy from food. And a tiny trace is carbon dioxide, which plants use for photosynthesis, turning sunlight, water, and air into life itself.
Water chemistry is a universe in itself. This simple molecule, H2O, is a universal solvent, able to dissolve more substances than any other liquid. And it has a wonderful quirk. It expands when it freezes. This is why ice floats, a rare property that allows life to survive in frozen lakes and oceans, insulating the water below. Let us not forget acids and bases. The pH scale measures their balance. Lemon juice is acidic. Soap is basic. Your own stomach uses powerful acid to digest food, a contained chemical reaction essential to your life. Chemistry also explains why some things simply do not mix. Oil and water famously stay separate. This is because water molecules are polar, clinging to each other, while oil molecules are nonpolar. They slide past each other like two different social circles at a party that never mingle. Even the colors we see are a product of chemistry. The green of a leaf comes from chlorophyll, a molecule that absorbs red and blue light and reflects green. The reds and purples of an autumn leaf come from other pigments, revealed as the chlorophyll fades. And the vast spectrum of smells and tastes, all chemistry. The scent of rain on dry earth, the aroma of coffee, the sweetness of vanilla. These are all molecules, drifting through the air, fitting into receptors in your nose and mouth, and painting a picture in your mind. For all its bewildering complexity, chemistry is guided by simple, elegant principles. Atoms seek stability. Electrons seek balance. Reactions seek equilibrium. From these gentle fundamental desires, the entire rich tapestry of the material world emerges. It is the quiet architect behind every breath you take, every sensation you feel. It is all happening at the atomic level. Countless tiny particles in a silent, intricate dance of making and breaking bonds. In a way, chemistry is the universe's love language.
It is how atoms connect, embrace, and create together. It is the reason a cloud can form, a tree can grow, and the world can be filled with such an astonishing variety of substance and beauty. Every reaction tells a story, whispered in molecules. Now, let us zoom out and consider two of the great, silent forces that shape our cosmos: light and gravity. They seem to belong to different worlds. One is ethereal, fleeting, bringing us warmth, color, and vision. The other is immense, patient, and persistent, quietly holding everything together, from your own body to the great slow waltz of galaxies. One travels at the ultimate cosmic speed limit, while the other is the very curvature of space-time itself. They do not seem to have much in common, yet they are two of the most fundamental characters in the story of the universe. Let's begin with light. It pours through your window, flickers on your screen, and reflects from the page of a book. But what is it really? Light is a form of electromagnetic radiation. It is a wave, an oscillation of electric and magnetic fields traveling through space. Unlike a sound wave, which needs a medium like air or water to travel, light is perfectly self-sufficient. It can journey through the absolute vacuum of empty space. It creates its own electric and magnetic fields as it goes, each one generating the other in a perpetual, graceful leapfrog. This is why light from the most distant stars can cross billions of light years of emptiness to reach our eyes. But here is the wonderful paradox of light. It is not just a wave, it is also a particle. This is the wave-particle duality at the heart of quantum physics. Light comes in discrete little packets of energy called photons. Each photon is a tiny,
massless quantum of light, always moving at the speed of light. In some experiments, light behaves like a spreading wave. In others, it acts like a particle, arriving one at a time. It is not choosing to be one or the other. It is simply being itself, a quantum entity that our classical language struggles to describe. Light travels at an incredible speed, roughly 300,000 kilometers or 186,000 miles per second, fast enough to circle the Earth more than 7 times in a single second. And yet this ultimate speed can be slowed. When light passes through a material like water or glass, it interacts with the atoms, being absorbed and re-emitted in a series of tiny delays that effectively slow its journey. But the moment it emerges back into a vacuum, it resumes its full, unwavering speed. And here, things become truly profound. According to Einstein's theory of relativity, the speed of light is not just fast, it is the absolute speed limit of the universe. Nothing with mass can ever reach it. And as you approach the speed, time itself begins to behave strangely. For a fast-moving traveler, time slows down relative to a stationary observer. This effect, called time dilation, means that astronauts on the space station age just a fraction of a second slower than we do on Earth. It's a tiny but real warping of time. And this warping of time and space brings us to gravity. For centuries, we thought of gravity as a simple pulling force. Newton's apple falls because the Earth pulls it. But Einstein revealed something far deeper. In his general theory of relativity, gravity is not a force at all. It is the curvature of the fabric of space-time caused by the presence of mass and energy. Imagine a stretched rubber sheet. If you place a heavy ball in the center, it creates a dip, a curve in the sheet. If you then roll a smaller marble nearby, it will curve inwards, not because the ball is pulling it, but because it is following the curve of the surface. That is gravity. Planets orbit the sun not because they are being pulled by an invisible rope, but because they are following the straightest possible path through the curved spacetime created by the sun's immense mass. Light, too, must follow these curves. When light from a distant star passes near a massive galaxy, its path is bent. This effect, called gravitational lensing, allows astronomers to use entire galaxies as cosmic telescopes, magnifying and revealing objects even farther away. Gravitational lensing has become one of our best tools for mapping the mysterious, invisible substance known as dark matter, which reveals its presence only through the gravitational curves it creates in spacetime.
Gravity also affects time. The stronger the gravitational field, the slower time flows. This is gravitational time dilation. Time literally ticks more slowly near the surface of the Earth than it does for a satellite in orbit. The effect is minuscule in our daily lives, but for a GPS system to work, its clocks must be programmed to account for this tiny relativistic slowing of time. One of the most beautiful confirmations of Einstein's theory was the detection of gravitational waves, ripples in the fabric of space-time itself, caused by cataclysmic events like the merging of two black holes. Predicted a century ago, these waves were first detected in 2015. They are incredibly faint, but they carry the sound of the cosmos, allowing us to listen to the universe in a completely new way. Despite its elegance, gravity remains the most mysterious of the forces. We have yet to unite it with quantum mechanics. The search for a quantum theory of gravity is one of the greatest quests in modern physics. So, as you rest, feel the gentle, persistent presence of gravity holding you, and know that the faint light filtering in from the stars has traveled across a universe shaped by that same force. Light
shows us where things are. Gravity dictates where they can go. One curves the map, the other travels across it. Together, they weave the great, silent, beautiful story of the cosmos. Welcome to our cosmic cul-de-sac, our own quiet neighborhood in the vast city of the Milky Way, the solar system. It is a charming and familiar place. A single, modest star at its center, orbited by a small family of planets, each with its own character, along with the supporting cast of moons, comets, and drifting dust. It may not be the most spectacular system in the galaxy, but it is ours. It is home. And as far as we know, it is the only place with quiet nights, soft blankets, and sleeping cats. Let us begin at the heart of it all, the sun. Our star is a radiant, life-giving sphere of plasma that contains over 99.8% of the entire mass of the solar system. Everything else, all the planets, moons, and asteroids combined, is just cosmic rounding error, the leftover dust and debris from the sun's formation. The sun is a yellow dwarf star. It shines because of nuclear fusion happening in its core, where immense pressure and heat crush hydrogen atoms together to form helium, releasing a torrent of energy. That energy can take over 100,000 years to journey from the core to the surface, but from there, it takes only 8 minutes to fly across space and gently warm the Earth. The sunlight that touched your face today began its journey from the sun's core long before human civilization began. Moving outward from the sun, our first stop is Mercury. A tiny, fast, and cratered world, it zips around the sun in just 88 days. With almost no atmosphere to protect it, its sun-facing side bakes at over 400 degrees Celsius, while its night side freezes to nearly negative 180 degrees Celsius. It is a world of silent, stark extremes. Next is Venus, often called Earth's twin due to its similar size. But it is a twisted twin, a vision of what can go wrong. Venus is a sweltering inferno. Its thick, toxic atmosphere of carbon dioxide has created a runaway greenhouse effect, trapping heat so efficiently that its surface temperature is a uniform 460 degrees Celsius, hot enough to melt lead. A day on Venus is longer than its year, and it spins slowly backwards. A truly inhospitable place. And then, with a sense of relief, we arrive home. Earth. A pale blue dot, shimmering with oceans, swirling with white clouds, and alive. Our planet exists in a delicate, precious balance. It has liquid water, a protective magnetic field, and an atmosphere that is just right. It is in the Goldilocks zone. Not too hot, not too cold. And we are its fortunate inhabitants. Earth is accompanied by its moon, a large and loyal companion that stabilizes our planet's tilt, creates the gentle rhythm of the tides, and lights up our nights with its soft, reflected glow. Our next stop is Mars, the red planet. With its rusty, dusty surface, giant extinct volcanoes, and the clear, dry beds of ancient rivers, Mars is a world of haunting beauty. Evidence strongly suggests that billions of years ago, it was a much warmer and wetter place with lakes and perhaps even oceans. Robotic rovers now slowly wander its surface, searching for clues of its past life and perhaps a future human presence. Beyond Mars, we find the asteroid belt. A vast, sparse ring of rocky debris, the leftovers from the formation of the planets. These are the cosmic crumbs that never managed to come together to form a world.
Past the asteroid belt, we enter the realm of the gas giants. First is Jupiter, the undisputed king of the planets. It is immense, more than 300 times the mass of Earth.
Its atmosphere is a swirling masterpiece of colorful cloud belts and storms, including the Great Red Spot, a hurricane larger than our entire planet that has been raging for centuries. Jupiter has no solid surface, and it is orbited by a vast family of at least 95 moons, some of which are worlds in their own right. Next is Saturn, the jewel of the solar system. It is famous for its breathtaking rings, a vast, shimmering disk made of countless particles of ice and rock, stretching for hundreds of thousands of kilometers, but in places only a few meters thick. Saturn is so light for its size that it would float in a bathtub if you could find one big enough. Further out, we find the ice giants. Uranus, pale blue and mysterious, spins on its side, perhaps knocked over by a massive collision in its distant past. This gives it the most extreme seasons in the solar system, with decades of darkness followed by decades of light. And finally, we reach Neptune, the last official planet. A deep, rich blue, it is a world of supersonic winds, the fastest in the solar system. One of its moons, Triton, orbits backwards and spouts geysers of nitrogen ice into the thin, frigid air. Beyond Neptune lies the Kuiper Belt, a vast, icy frontier, home to dwarf planets like Pluto. Once our ninth planet, Pluto was revealed by the New Horizons mission to be a surprisingly complex world, with mountains of water ice, glaciers of nitrogen, and a vast, heart-shaped plain. And even further out, surrounding the entire solar system, is the hypothetical Oort cloud, a vast, spherical shell of trillions of icy comets orbiting silently in the deep freeze of interstellar space. And all of this, planets, moons, asteroids, and comets, is held in a gentle gravitational embrace, all spinning together through the dark, a tiny, precious, and beautiful system, our home in the vastness of the cosmos. The two Voyager spacecraft, launched in the 1970s, have now crossed into interstellar space, carrying with them golden records, a message in a bottle from our world to whatever may find it in the distant future. Our solar system is just one star's family in a galaxy of billions, but it is more than enough to fill us with a lifetime of wonder. From the silent, dust-red plains of Mars to the swirling storms of Jupiter, it is a reminder that even our own cosmic backyard is filled with endless beauty and mystery. It is who we are, a collection of worlds, large and small, light and dark, all spinning together in the gentle grip of our sun. Stars are a bit like people. They are born, they live their lives, and they eventually fade away. Some depart quietly, while others go out in a blaze of glory that can outshine entire galaxies. The life story of a star is the story of how the universe builds itself, recycles its materials, and seeds the cosmos with the ingredients for new life. A star might look like a calm, twinkling point of light, but it is a raging furnace of nuclear fusion, a sphere of superheated plasma held in a delicate balance between the inward crush of gravity and the outward push of its own energy. The story of a star begins in a nebula, a vast, cold cloud of gas and dust. These cosmic nurseries are scattered throughout our galaxy. Something, perhaps the shock wave from a nearby supernova, causes a dense clump of this cloud to begin to collapse under its own gravity. As it contracts, it heats up, forming a glowing ball called a protostar. Gravity continues to pull material inward, and the core becomes hotter and denser. When the temperature and pressure reach a critical point, millions of degrees, nuclear fusion ignites. Hydrogen atoms begin to fuse into helium, releasing an immense amount of energy. At this moment, the protostar becomes a true star, shining with its own light. This newfound energy pushes outward, perfectly balancing gravity's inward pull, and the star enters a long, stable period of its life. A star's destiny is written almost entirely by its mass. Small stars, known as red dwarfs, are the most common type. They are frugal with their fuel, sipping their hydrogen so slowly that they can live for trillions of years. Since the universe is only 13.8 billion years old, not a single red dwarf has ever died. Our Sun is an average-sized star. It has been shining for about 4.5 billion years and has about 5 billion more to go. It converts about 600 million tons of hydrogen into helium every single second. When the hydrogen in the Sun's core runs out, fusion will slow and gravity will begin to win. The core will contract and heat up, causing the outer layers of the Sun to expand dramatically. The Sun will swell into a red giant, so large it may engulf Mercury and Venus. During this phase, it will begin fusing helium into carbon and oxygen.
Eventually, these outer layers will drift away into space, creating a beautiful, glowing structure called a planetary nebula. At the center, the hot, dense core will remain a white dwarf, about the size of Earth. A white dwarf no longer produces new energy. It is a stellar ember, glowing with leftover heat, and it will spend trillions of years slowly, peacefully cooling and fading into a cold, dark object called a black dwarf. But for the most massive stars, the end is far more dramatic. Stars more than 8 times the mass of our Sun live fast and die young. They burn through their fuel at a furious rate, fusing heavier and heavier elements in their core, helium to carbon, carbon to neon, and so on, all the way up to iron. But fusing iron does not release energy, it consumes it. When an iron core builds up, the star's furnace shuts down. Without the outward pressure of fusion, gravity takes over instantly and catastrophically. The core collapses in a fraction of a second, triggering a titanic explosion known as a supernova. For a few weeks, a single supernova can outshine its entire galaxy. This explosion is not just an act of destruction, it is an act of creation. The incredible heat and pressure forge all the elements heavier than iron: gold, silver, platinum, uranium. The gold in a wedding ring, the iron in your blood, all of it was created in the final, violent moments of a long-dead, massive star and scattered across the galaxy. What's left behind depends on the mass. For some, the core collapses into a neutron star, an object the size of a city but with more mass than our Sun. It is so dense that a single teaspoon of its material would weigh 1 billion tons. Some neutron stars spin rapidly, sweeping beams of radiation across space like a cosmic lighthouse. We see these as pulsars. But if the original star was massive enough, the core collapses completely, with no force in the universe strong enough to stop it. It collapses into a black hole, a region of space-time where gravity is so intense that nothing, not even light, can escape. Stars are the engines of the cosmos. Their lives create the elements, their light warms planets, and their deaths seed the universe with the raw materials for new stars, new planets, and new life. When you look up at the night sky, you are looking into the past. Every star is a message of light that has traveled for years, centuries, or millennia to reach you. Some of the stars you see may have already died, their final light just now arriving. Others are just beginning their long, luminous journey. They are silent, glittering reminders of the vast, beautiful, and eternal cycle of creation that fills our universe. Galaxies are the great cities of the cosmos. Sprawling, luminous metropolis is built not from steel and glass, but from billions of stars, swirling clouds of gas, and a vast, invisible scaffolding of dark matter.
If stars are the individual homes, then galaxies are the vast, gravitationally bound neighborhoods where the cosmic story unfolds on the grandest of scales. Take a moment and try to hold the idea of a galaxy in your mind. A single galaxy can contain hundreds of billions of stars. Each of those stars could host its own family of planets, and there are perhaps 2 trillion galaxies in the observable universe. The numbers are beautifully, peacefully incomprehensible. Our home is the Milky Way, a barred spiral galaxy. It has a bright, elongated central bar of stars with graceful spiral arms curving outward like a cosmic pinwheel. We are located about 2/3 of the way out in one of these quiet, residential arms. When you look up on a clear, dark night and see that faint, hazy band of light stretching across the sky, you are looking into the dense, crowded heart of our own galactic city. At the very center of the Milky Way, there lies a supermassive black hole named Sagittarius A star. It has a mass of about 4 million suns, and it sits there silently while entire stars orbit it at incredible speeds. We have even managed to take a picture of its shadow, a dark silhouette against the glowing gas swirling around it. Galaxies come in many shapes and sizes. Besides spiral galaxies like ours, there are elliptical galaxies. These are smooth, featureless ovals of stars, generally containing older, redder stars with very little new star formation. They are the quiet, old cities of the universe. And then there are irregular galaxies, which have no defined shape at all. They are often chaotic and messy, their forms twisted by gravitational encounters or collisions with other galaxies. Galaxies are not shy about interacting. Over cosmic timescales, galactic collisions are common. But because the space between stars is so vast, individual stars rarely collide. Instead, the 2 galaxies pass through each other like ghosts, their shapes distorted by gravity, triggering spectacular bursts of new star formation. Our own Milky Way is on a collision course with our nearest large neighbor, the Andromeda Galaxy. They are hurtling towards each other and are expected to begin merging in about 4 billion years. The night sky during that long, slow collision will be a breathtaking spectacle of 2 galaxies dancing together, eventually settling into a new, larger elliptical galaxy. Galaxies themselves are not distributed randomly through space. They are gathered together by gravity into groups, clusters, and superclusters. The Milky Way is part of the local group, which is in turn part of the Virgo supercluster. And these superclusters are not random blobs either. They are arranged in a vast interconnected network of filaments and walls surrounding enormous, nearly empty regions called voids. This is the cosmic web, the largest known structure in the universe, a breathtakingly beautiful web-like pattern of light and gravity stretching across billions of light years. It was by observing galaxies that we first learned the universe is expanding. In the 1920s, Edwin Hubble noticed that almost all galaxies are moving away from us, and the farther away they are, the faster they are moving. This was the first evidence for the Big Bang. Recently, a strange discrepancy has emerged, known as the Hubble tension. Measurements of the expansion rate using nearby galaxies give one value, while measurements using the faint afterglow of the Big Bang give a slightly different one. This subtle disagreement might be pointing towards new, undiscovered physics, a deeper secret about our expanding universe. So the next time you see a picture of a distant galaxy, remember what you are seeing. You are seeing an island of billions of stars held together by gravity, perhaps with its own supermassive black hole at the center. And the light from that galaxy may have been traveling for millions or billions of years to reach us, a postcard from the deep past. And our own Milky Way, our own luminous home, is just one of trillions, a single glowing swirl in a universe filled with them. And you are a part of it, a conscious piece of a galaxy looking out and wondering. Let us play a gentle game of cosmic hide and seek. Imagine looking out into the universe. You see stars, galaxies, nebulae, a sky glittering with light. But what if I told you that everything you can see, all the luminous matter, makes up only 5% of the total mass and energy in the universe? The other 95% is hidden, invisible, and mysterious. We now turn to the first part of that hidden majority, dark matter. The name sounds dramatic, but it simply means that this matter does not interact with light. It does not emit, absorb, or reflect it. It is utterly transparent and invisible. We cannot see it. We cannot touch it. It passes through us, through the earth, as if we are not even here. But it has one crucial property. It has mass, and therefore it has gravity. And that is how we know it exists. The discovery of dark matter began with a puzzle. When astronomers observed spiral galaxies, they saw that stars on the outer edges were moving just as fast as stars near the center. According to the laws of gravity, they should have been moving much more slowly. For them to be moving so fast without flying off into space, there had to be a huge amount of extra unseen mass in the galaxy, providing the extra gravitational glue to hold them in orbit. This invisible mass was dubbed dark matter. The evidence is now overwhelming. We see its effects in the way galaxies cluster together and in the way its gravity bends the light from distant objects through gravitational lensing.
The faint afterglow of the Big Bang, the cosmic microwave background, also carries the imprint of dark matter from the very early universe. So what is it? This is one of the greatest unsolved mysteries in all of science. We know what it does, but we do not know what it is made of. The leading candidates are hypothetical particles with names like WIMPs, weakly interacting massive particles, or axions. Scientists have built incredibly sensitive detectors deep underground, shielded from all other radiation, hoping to catch the rare, fleeting signal of a single dark matter particle bouncing off a normal atom. So far, the search continues. Dark matter does not clump together to form stars or planets. Instead, it seems to form a vast spherical halo around galaxies, an invisible scaffold upon which the visible galaxy is built. Without dark matter, galaxies as we know them would never have formed. The beautiful spirals and clusters we see would not exist. Dark matter is the quiet, invisible architect of the cosmos. And there is about 5 times more dark matter in the universe than there is normal visible matter. We, the stars and the planets, are the cosmic exception, not the rule. The universe, it seems, is mostly made of something we cannot see. But there is no need to feel crowded. This dark matter passes through you as you rest, as harmless and gentle as a ghost. It is the silent, gravitational soul of our universe, holding the stars in their courses and reminding us that the greatest mysteries are often hidden in plain sight. It is all around us, this dark matter, silently anchoring the stars, weaving the cosmic web, and whispering that even in the dark, there is structure, there is beauty, and there is still so much to learn. The universe has always been in motion. Even as the stars seem to hang serenely in the sky,
a hidden force is at work, pushing everything apart. Space itself is expanding, and not only that, the expansion is accelerating. The cause of this cosmic acceleration is the second and larger part of the universe's hidden majority. It is an elusive, invisible pressure called dark energy. Again, the name is more dramatic than the reality. Dark energy is not ominous. It is simply a term for the unknown energy that seems to be inherent in the fabric of space itself, causing it to stretch. The idea began with Einstein. When he first formulated his theory of gravity, his equations suggested the universe should either be expanding or contracting. To match the belief at the time that the universe was static, he added a cosmological constant, a kind of repulsive force to balance gravity. When Edwin Hubble later proved the universe was expanding, Einstein called the constant his greatest blunder. But he may have been right for the wrong reason. For decades, astronomers assumed that the expansion, while real, must be slowing down as the mutual gravity of all the galaxies pulled back on each other. But in the late 1990s, by observing distant supernovae, they found something shocking. The expansion of the universe is not slowing down. It is speeding up. Something is pushing everything apart, overwhelming gravity on the largest scales. That something is dark energy. It is now believed to make up about 68% of the total energy content of the universe. Normal matter is less than 5%. Dark matter is about 27%. The cosmos is dominated by these two invisible components, dark matter pulling things together and dark energy pushing them apart. The simplest explanation for dark energy is that it is the energy of empty space itself, the cosmological constant that Einstein first proposed. As space expands, more empty space is created, and with it, more of this repulsive energy, causing the expansion to accelerate. The very presence of dark energy dictates the ultimate fate of our universe. If it remains constant, the universe will expand forever. Galaxies will drift further and further apart, their light eventually redshifting beyond our ability to see them. The cosmos will cool and fade into a cold, dark, and silent state known as the Big Freeze.
This is the most likely scenario based on what we know now. The universe will not end in a fiery crunch, but with a long, slow, peaceful fade into darkness over trillions upon trillions of years. We cannot see dark energy. We cannot touch it or bottle it in a lab. We only see its effect on the universe as a whole, a gentle, persistent push woven into the fabric of space-time itself. Unraveling this mystery is one of the biggest goals of modern cosmology. Massive new telescopes are being built to map the universe with unprecedented precision, hoping to find a clue to the nature of this mysterious energy. Dark energy is a profound reminder of how much we still have to learn. At the very edge of our knowledge, we find a force that dominates the cosmos, yet defies all our current explanations. It is both deeply humbling and wonderfully exciting. The universe isn't a solved puzzle. It is a living, breathing enigma. And as you rest tonight, know that the very space around you is gently, silently, relentlessly stretching, driven by this invisible whisper, shaping the future of everything. The universe was not always this vast, dark, and speckled with stars. If we could rewind the great cosmic clock all the way back, we would arrive at a moment of unimaginable beginning. This is the story of the Big Bang. The name is a little misleading. It was not an explosion in space like a firework. It was the beginning of space itself. It was the moment that time, space, matter, and energy burst into existence from a state of incomprehensible density and heat. It was not something that happened in the universe. It was the happening of the universe.
How do we know this? The most powerful clue is the oldest light in the universe, the cosmic microwave background, the CMB for short. It is a faint, cold glow of microwave radiation that fills all of space, coming from every direction. It is the afterglow of the universe's birth. In the beginning, for the first 380,000 years, the universe was a hot, dense, opaque fog of particles and radiation. Light was trapped, constantly bouncing off free-roaming electrons. But as the universe expanded, it cooled. Eventually, it became cool enough for protons and electrons to combine and form the first neutral atoms. At this moment, the universe suddenly became transparent. The light that was trapped was finally set free to travel unimpeded through space. That ancient light has been traveling ever since. Its wavelength, stretched by the expansion of the universe, it has cooled to a mere 2.7 degrees above absolute zero. This is the cosmic microwave background. It is the baby picture of the universe. And when we look at it with our radio telescopes, we see that it is not perfectly uniform. It has tiny, minuscule ripples in temperature. These tiny fluctuations were the seeds of all future structure. The slightly denser regions had slightly more gravity, and over billions of years they pulled in more and more matter, eventually growing into the galaxies and clusters of galaxies we see today. The entire cosmic web is a grown-up version of the faint ripples in this ancient light. Let's rewind even further. In the very first fraction of a second, the universe was a maelstrom of energy. And then, according to our best theories, something incredible happened. A period of super-fast expansion called cosmic inflation. In less than a trillionth of a second, the universe expanded exponentially, ballooning from a subatomic size to something enormous. This smoothed out the universe and laid the groundwork for the structures we see. After inflation, the universe continued to expand and cool. Within the first few minutes, the first atomic nuclei were forged, mostly hydrogen and helium. These are the raw materials from which everything else would be built. After the CMB was released, the universe entered a period known as the Cosmic Dark Ages. There were no stars yet, no galaxies, just vast, dark clouds of hydrogen and helium drifting through space. This lasted for a few 100 million years until gravity, working patiently in the dark, pulled enough gas together to form the very first stars. When these first stars ignited, they flooded the universe with light, ending the Dark Ages and beginning the cosmic dawn. From there, the story we know unfolds. Galaxies formed and merged. Stars lived and died, enriching the universe with heavier elements. Planets formed, and on at least one small, rocky world, life emerged, and eventually developed minds capable of looking back across 13.8 billion years and piecing together this incredible story. The Big Bang Theory is not a guess. It is supported by overwhelming evidence: the expansion of the universe, the existence and properties of the CMB, and the abundance of light elements we observe today.
But what came before the Big Bang? Here, science reaches its current limit. Some say time itself began then, making the question of before meaningless. Others imagine a cyclical universe, or a multiverse of countless beginnings. For now, it remains a beautiful mystery. But when you gaze at the stars, know that you are witnessing the echoes of that singular beginning, a moment when everything you know, everything you are, was contained in a point smaller than a grain of sand. And from that point, all of this wonder bloomed. You carry a piece of that beginning, within you still. Black holes. The very words conjure images of cosmic monsters, of ultimate darkness. But the reality of black holes is even more fascinating than the fiction. At its core, a black hole is an object whose gravity is so powerful that it has warped space-time into a trap from which nothing can escape. Once something crosses a certain boundary, the event horizon, it can never leave. The event horizon is not a physical surface. It is simply the point of no return, the point where the gravitational pull becomes infinite and escape velocity exceeds the speed of light. Most black holes are born from the deaths of massive stars. When a star many times the mass of our sun runs out of fuel, its core collapses under its own immense gravity. It compresses into a point of theoretically infinite density, called a singularity. This singularity is where our current understanding of physics breaks down. We would need a theory of quantum gravity to truly know what happens at the center. There are stellar mass black holes, just a few times the mass of our sun. And then there are the giants, supermassive black holes, which sit at the heart of nearly every large galaxy, including our own. These can weigh millions or even billions of times the mass of the sun. As you approach a black hole, strange things happen to time. Gravity warps time, so the stronger the gravity, the slower time flows. If you were to hover just outside the event horizon, time for you would pass much more slowly than for someone far away. An observer watching you would see you move in slow motion, appearing to freeze as you reached the horizon. From your own perspective, however, you would cross it without any issue, assuming you weren't torn apart first by the extreme tidal forces in a process with the wonderful name of spaghettification, where the difference in gravity between your head and your feet would stretch you into a long, thin strand. It is a myth that black holes are cosmic vacuum cleaners, sucking everything in. You can orbit a black hole safely, just as planets orbit the sun. If our sun were magically replaced with a black hole of the same mass, the Earth's orbit would not change at all. It would just get very dark and very cold. In fact, the region around a black hole can be one of the brightest places in the universe. As gas and dust are pulled in, they form a swirling, superheated accretion disk around the black hole. Friction in this disk can make it glow with incredible intensity, sometimes outshining entire galaxies. For a long time, black holes were just a strange prediction of Einstein's theories, but we now have overwhelming proof of their existence. We have watched stars orbit them, we have detected the gravitational waves from their collisions, and in 2019, the Event Horizon Telescope collaboration gave us our first direct image, the shadow of the supermassive black hole at the center of the M87 galaxy. The physicist Stephen Hawking made a remarkable discovery. Black holes are not entirely black. Due to quantum effects near the event horizon, they very slowly emit a faint glow of radiation, now called Hawking radiation, which means that black holes can, over unimaginable timescales, slowly evaporate
and fade away. Even these most permanent-seeming objects in the universe are not forever. Black holes push our understanding of reality to its absolute limits. They are where gravity and quantum mechanics meet in a way we do not yet understand. They are laboratories for the most extreme physics in the universe, mysterious, powerful, and endlessly fascinating. They are silent reminders that the universe is not only stranger than we imagine, but stranger than we can imagine. What if this universe, with its specific laws of physics, its stars, and its galaxies, is not the only one? What if our reality is just a single bubble in a vast cosmic foam of other universes? This is the idea of the multiverse. It is a concept that lives on the very edge of theoretical physics. But it is not just science fiction. It arises naturally from some of our best and most successful theories. One version comes from the theory of cosmic inflation. In many models, the rapid expansion of the early universe doesn't stop everywhere at once. It stops in patches, creating bubble universes like our own. Meanwhile, the space between these bubbles continues to inflate eternally, constantly spawning new universes, each potentially with its own unique physical laws. Another version comes from quantum mechanics. The many worlds interpretation suggests that every time a quantum measurement is made, the universe splits into multiple branches, one for each possible outcome. In one universe, the particle went left. In another, it went right. This creates a constantly branching tree of parallel realities, with countless versions of you living out every possible life path.
And a third version arises from string theory, which proposes that there is a vast landscape of possible ways the universe could be, each corresponding to a different set of physical laws. We just happen to live in the one where the conditions are right for life to exist. This is sometimes called the anthropic principle. Do we have any evidence for the multiverse? Not directly. By their very nature, these other universes may be forever beyond our reach. But scientists have looked for indirect signs, like faint bruises in the cosmic microwave background that could have been caused by a collision with another bubble universe in the distant past. The multiverse idea is speculative, and it raises deep philosophical questions about identity and choice. But it is a beautiful and humbling thought. It suggests that reality is bigger, stranger, and more layered than we could ever have imagined. It doesn't diminish our universe. It places it in an even grander context. It nudges open the door to a reality where anything that can happen does happen, somewhere, in some distant fold of the cosmic tapestry. So, as you rest, you can consider that there may be countless other versions of you resting as well, scattered across an infinite sky of possibilities, each one a whisper of what could be, each one part of a great cosmic chorus, singing softly just beyond the edge of what we can see. There is a gentle irony in how we perceive time. We measure it, schedule it, and feel its passage second by second. We treat it like a fixed, universal ruler. But the deeper we look into physics, the more we find that time is a slippery, relative, and profoundly strange thing. Our modern understanding of time began with Einstein. His theories of relativity showed that time is not absolute. It is woven together with space into a single fabric, space-time. And this fabric can be stretched and warped. The faster you move through space, the slower you move through time. This is time dilation. It is a real effect, measured in astronauts and accounted for in the GPS satellites that orbit our Earth. Gravity also warps time. The stronger the gravitational field, the slower time flows. Time ticks ever so slightly faster on a mountaintop than it does at sea level. Near a black hole, this effect becomes extreme, with hours passing for a nearby observer while millennia pass for someone far away. This pliability of time leads to the question of time travel. Traveling to the future is in principle possible. If you were to travel near the speed of light and then return, you would find that far more time had passed on Earth than for you. Traveling to the past, however, is much more problematic, leading to paradoxes like the famous grandfather paradox. Most physicists believe it is likely impossible. So why does time seem to have such a strong, unbreakable arrow, always moving from past to future? Why do we remember the past, but not the future? The answer seems to lie in the second law of thermodynamics. This law states that entropy, a measure of disorder, always tends to increase in a closed system. Eggs break, but don't unbreak. Cream mixes into coffee, but doesn't unmix. The universe began in a very low entropy, highly ordered state, and the arrow of time is simply the universe's long, slow, and inevitable journey towards a state of greater disorder. This gives time its direction. But some physicists now wonder if time is fundamental at all. Perhaps it is an emergent property, something that arises from a deeper, timeless level of quantum reality, just as the sensation of temperature emerges from the motion of countless individual atoms. In this view, the smooth, flowing river of time we experience is an illusion, a macroscopic approximation of something much stranger happening at the most fundamental level. But whether time is fundamental or emergent, it is the canvas upon which our lives are painted. It turns moments into memories, gives music its rhythm, and seasons their gentle flow. So as you rest, feel the steady, rhythmic beat of your own heart. It is your personal clock, ticking away in a universe where time itself is one of the deepest and most beautiful mysteries of all. If the universe had a voice, it would speak in the language of light, not just the visible light our eyes can see, but the entire spectrum of electromagnetic waves that hum and whisper across the cosmos. Radio waves from cold gas clouds, infrared from newborn stars, X-rays from the hearts of galaxies. This is how we have learned almost everything we know about the universe. Light is our cosmic messenger. Light travels at the ultimate speed limit, about 300,000 kilometers per second. And because this speed is finite, when we look out into space, we are looking back in time. The light from the moon is a second old. The light from the sun is 8 minutes old. The light from the nearest star system, Alpha Centauri, is 4 years old. And the light from the Andromeda Galaxy has been traveling for 2.5 million years to reach us. The most powerful telescopes can see galaxies whose light has traveled for over 13 billion years, allowing us to see the universe as it was when it was just a fraction of its current age. Light also carries the chemical fingerprints of the objects it comes from. Every element absorbs and emits light at specific, characteristic wavelengths. By analyzing the light from a distant star, we can tell what it is made of, how hot it is, and how fast it is moving. This is how we know the sun is made of hydrogen and helium, and how we can detect water vapor in the atmospheres of planets orbiting other stars. Light is our cosmic messenger. In every glimmer, every shimmer, every soft beam and gentle glow, you are witnessing the fundamental force that has revealed to us the birth of the universe, and will one day show us how far there is still to go. And so, our cosmic tour gently comes to a rest. We have drifted from the strange dance of quantum particles to the silent waltz of galaxies. We have touched upon the birth of stars, the mystery of black holes, and the very fabric of time. We have pondered what was, what is, and what might be, across the vast and beautiful expanse of the cosmos. It is a great deal to hold in the mind. If you are still awake, I hope you found this a peaceful kind of wonder. And if you drifted off to sleep somewhere between dark matter and planetary nebulae, then our mission was a success. Either way, you spent a little time with the universe tonight. Before you float away completely, I would love to hear where this sleepy broadcast has found you. What time is it for you right now? Let me know in the comments below. It is a quiet wonder to imagine all of us connected for a moment under different skies. And if this journey brought you any peace or calm, please consider leaving a like or subscribing. It is a small gesture that truly helps support this channel and allows these gentle explorations to continue. Thank you for joining me on this voyage. Rest well, dream deeply, and remember that the universe is vast, beautiful, and always waiting, silently, to be wondered about. Good night.